Welcome to Brain Vision.
To do the proof for part A, we're going to consider the fact that the change in energy for the hydrogen delta H is equal to minus mu sub H, which is the reduced mass, times the constant of Coulomb, K squared, times the charge of the electron to the fourth divided by 2 H bar squared. And this is multiplied by the difference of 1 over the final state squared minus 1 over the initial state squared. And the change in energy for deuterium is the exact same, except this time we have mu sub d, the reduced mass for deuterium. The other relationship we have for delta E, the change in energy for hydrogen, is defined as H times C divided by the wavelength from the change in that energy. And then the same thing for lambda d, or for the change in energy for deuterium, except this time we have lambda sub d. So to do this proof, we're going to take the ratio of delta E sub H, we'll call this part A. So we're going to take delta E H divided by delta E sub D. Well, from the two leftmost equations, everything in the equation is the exact same except for the reduced mass constant. So we're just going to be left with the ratio of the reduced mass constants. Negative signs cancel, so this is just mu sub H divided by mu sub D. And then from the two rightmost equations, Planck's constant and the speed of light c both cancel, and so we are left with lambda d over lambda h, since the energies are inversely proportional to the wavelength values. So we can rewrite lambda d in terms of the two reduced masses. So we have lambda d is equal to mu sub h over mu sub d. So now you're maybe starting to recognize why we did it this way relative to the proof equation that we're trying to find. Multiplied by lambda h. So now, if I take lambda h minus lambda d, which is what the equation that we're trying to prove has on the leftmost side, I can replace lambda d with that equation there. So this gives me lambda h minus mu sub h over mu sub d times lambda h. So we can pull the lambda h out front, since both equations have lambda h values in them. So this gives us lambda h multiplied by 1 minus the ratio of the reduced mass for hydrogen, mu sub h, divided by the reduced mass for deuterium, mu sub d. And that's the equation we were asked to show, so that is our proof. We can box that in. Part B wants us to find an actual numerical value for this, considering the fact that it says that lambda h is equal to 656.3 nanometers. So we know what lambda h is in this equation, so we just need to find mu sub h over mu sub d. So we'll call this part B. So mu sub h divided by mu sub d is the value we need to find, and then we can plug that into our equation and calculate lambda h minus lambda d. So mu sub h, by definition, is equal to, since hydrogen is made up of electron and a proton, the reduced mass of hydrogen is the mass of the electron times the mass of the proton divided by the mass of the electron plus the mass of the proton. So that's the reduced mass of hydrogen. And then we're going to divide this by the reduced mass of deuterium, which is the mass of the electron times the mass of deuterium divided by, oh, this is the mass of the electron above, there we go, divided by the mass of the electron plus the mass of deuterium. So all these values are just a constant, and we're going to use the units. You could use units of kilograms here, or you could use atomic units. It doesn't matter because the units are going to cancel out. We're just taking a ratio. So plugging in these values, we find that this is equal to 0.999 728. So if we plug that in for our mu sub h over mu sub d value up above in the that answer that we found boxed in, we plug in a value for lambda h that was given as 656.3 nanometers, we find that lambda h minus lambda d comes out to equal 0.179 nanometers. And we can box that in as our solution for part B.